In physics, we recognize that there are three types of collisions. And the first type is called perfectly inelastic. In a perfectly inelastic collision, the objects stick together after the collision. Okay, now it could be a completely mundane situation mechanically. For example, I have these two carts. This cart here has a nail, this cart here has a close clip. And then what I'm going to do is line the two carts up like so appropriately and then collide them into each other such that they stick together after the collision. So this right here is a simple example of a perfectly inelastic collision. Now it's the non-conservative force of friction between the nail and the close clip, for example, that's holding the two carts together, so then therefore there is heat loss. Now, a more exotic situation would be, say, nuclear fusion. In nuclear fusion, you have protons and neutrons coming together by means of the strong nuclear force to build, if you will, increasingly heavier and heavier atomic nuclei. Those types of collisions are perfectly inelastic as well. And then secondly, we have what is simply called the inelastic collision. In an inelastic collision, the objects bounce off of each other after the collision. Okay, now I can go ahead and collide the carts together by means of the elastic bands. For example, like so. And then when the objects bounce off of each other, this right here is an inelastic collision. Okay, now the total amount of kinetic energy of the carts before the collision is a little greater than the total amount of kinetic energy after the collision. And the reason for that is because during the collision itself, due to friction, there's a little bit of heat loss. Some of that energy, by the way, is converted into a sound wave. I mean, after all, you can hear the collision, like so. So where did that energy come from? It came from the original kinetic energy of the carts. So it's a realistic situation in the sense that there is heat loss. However, if the time of the interaction between the two carts is small, after all, these two carts, for example, are only in contact with one another for a split second, then the amount of energy that is lost as heat during that time interval is very small, especially compared to the original kinetic energy of the carts. So then therefore the third type of collision is an approximation. It's called an elastic collision. Depending upon the textbook, it's sometimes referred to as a perfectly elastic collision. In an elastic collision, it's an approximation. We assume that the time of the interaction between the two objects is negligible, so then therefore the amount of heat loss is negligible. So then therefore the total kinetic energy of the carts before the collision is assumed to be the same as the total kinetic energy of the carts after the collision. As we'll see in simple examples later on, this is a perfectly valid assumption to make as long as the time of the interaction is small. So we have this third type of collision. Once again, depending upon the textbook, it'll either be referred to as elastic, sometimes called perfectly elastic. In an elastic collision, once again, the objects bounce off each other, but we consider the heat loss to be negligible. But we consider the heat loss to be negligible. As we'll see with simple examples later on, this is a perfectly valid assumption to make. Okay, now we start to work our way through the different types of collisions here, both for situations involving one and two-dimensional cases. We're going to begin with the one-dimensional perfectly inelastic collision. We'll take a look at two situations. So let me go ahead and do some erasing here. We're now going to go ahead and access the first of those two examples. And as we work our way through these problems involving the one-dimensional perfectly inelastic collision, you're going to see lots of similarities between these types of collisions and explosions, which of course we did earlier. All right, so let's begin to take a look at the one-dimensional perfectly inelastic, so these stick together, collision. Okay, the first of the two problems is as follows. We're going to do a couple of parts to it. We're going to have two objects undergo a perfectly inelastic collision in one dimension. The first object has a mass of 1 kilogram and an initial speed of 1 meter per second when it collides with a second object which has a mass of 2 kilograms and it's initially at rest. So using my carts here and some weights and so on and so forth, I will go ahead and simulate this collision for us here as we begin to work our way through the example. Okay, let me set this up here like so. Okay, now in part A of the problem, there's a couple of parts to this. We're going to go ahead and find the final velocity. Okay, so here's how we begin to set this up. Once again, we assume it all takes place on a horizontal frictionless surface, so the sum of the external forces is 0. Okay, so we have our first object here, M1, with a mass of 1 kilogram. It's initially moving to the right-hand side with an initial velocity V1 naught that's given to us as 1 meter per second. Okay, here's the second object, mass M2. This one here has a mass of 2 kilograms. This object is initially at rest, so V2 naught is equal to 0. And then the two objects collide and stick together in the perfectly inelastic collision. So here's M1 and M2 stuck together, and then therefore they have the same common final velocity, like so V final. That's the unknown here in part A of the example. Okay, and then much like we did for explosion problems, we just set up our conservation equation. That is, change in momentum of number 1 plus change in momentum of number 2 is equal to 0. This is a one-dimensional problem, so then therefore we don't need the vector symbology. Okay, let's just start filling in the terms, and you go object by object. So for example, when we take a look at, first of all, object number 1, its final momentum after the collision is going to be its mass multiplied by the final velocity. So M1 times V final. And then minus its initial momentum before the collision, which is M1 V1 naught. And then we add to that the change in momentum now of object number 2. So you separate the objects when using this equation, and you just examine each one as you go. So for object number 2, its final momentum after the collision is going to be M2 times the same V final, like so. And then minus the initial momentum of number 2, which is equal to 0 because that object begins at rest. And now we just solve for V final. So to solve for V final, what I'm going to do is I'm going to take the M1 V1 naught and move it to the other side, like so. And then if you add these two terms together, where the V final is common to both, I can then do a little bit of factoring here as I go like so, and I end up with this expression here. Here's what this expression says. All the momentum of the system before the collision is equal to all of the momentum of the system after the collision. And then to solve for V final, let's just divide the parentheses to the other side. Like so, and now we plug in our numbers. So 1 times 1 in the numerator divided by 1 plus 2, so ultimately this ends up being 1/3, or 0.33 meters per second. And now here's how I'll go ahead and demonstrate this using my carts. So let's go ahead and make the mass of this cart here 2 kilograms, and this guy here is 1 kilogram. And I'm going to line the closed clip up with the nail once again like so. And then after I let go of this guy, he's moving in that direction at 1 meter per second. They then undergo the perfectly inelastic collision, and after the collision, the two carts move together at 0.33 meters per second. So that basically looks more or less like this, like so. Okay, now there's a second part to the problem. Let me move my file. Okay, as I mentioned earlier, when talking about the perfectly inelastic collision, the force that's causing everything to stick together here is friction, which is non-conservative. So then therefore energy is lost as heat. In the case of the perfectly inelastic collision, calculating the heat loss is easy to do. So part B of the problem asks for how much energy is lost as heat. Here's how I'm going to set this up. The amount of heat loss, let me write it like this, delta E, is going to be the change in kinetic energy of cart number 1 plus the change in kinetic energy of cart number 2. If this quantity here is equal to 0, this would then mean that there is no heat loss, but there is in the case of the perfectly inelastic collision because once again the frictional force is what's causing these objects to stick together. So ultimately, we're going to just calculate this number here by filling in all of these terms. When we do, we should end up with a negative number, which means that the final energy of the system is less than the initial energy of the system. So then therefore that negative number is the heat loss. So now let's just go ahead and fill in terms here. So change in kinetic energy of cart number 1. So after the collision, its final kinetic energy is 1/2 m1 times v final squared. And then minus its initial kinetic energy prior to the collision, 1/2 m1 v1 naught squared. And then add to that then the change in kinetic energy of cart number 2. So its final kinetic energy is 1/2 m2 v final squared, and then minus its initial, which is equal to 0, because remember that cart number 2 begins at rest. And now nothing cancels out here or anything like that. All that we do is just fill in all of the numbers here, and we should end up with a small negative number. So let's now see what happens. So 1/2 times 1 times 0.33 squared, and then minus 1/2 times 1 times 1 squared, plus 1/2 times 2 times 0.33 squared, and then minus 0. And ultimately you do end up with a small negative number here. It's about negative 0.34 joules. So the amount of energy that was lost as heat is 0.34 joules. Simple as that, okay? Okay, as you can see, there's really not much to the one-dimensional perfectly inelastic collision, so then therefore as a second problem we'll do an application. Let me do some erasing. Okay, the application that we'll look at here in this second problem in just a moment is a situation involving what is called a ballistic pendulum. A ballistic pendulum is a tool that is used in forensic science. Now, forensic scientists are tasked with using the scientific method to ultimately then solve a crime. So the reason why forensic scientists are called scientists is because they are using the scientific method to solve a problem. It's not a problem involving nature. Instead, in this case, it's a problem involving solving a crime. So they're using the tools of science to solve crimes. You see this depicted all the time in various TV shows like CSI and NCIS and so on and so forth. The investigative team that is using the tools of science to help solve crime, those people are forensic scientists. One of the basic aspects of forensic science is a subset, if you will, called ballistics. Where in ballistics, you basically examine the physics of what happens when a weapon is fired. Ultimately, one of the most important numbers that you can know about a gun, for example, when it's fired, is what's called its muzzle velocity. This is the speed of the projectile when it emerges from the barrel of the gun. Assuming that the forensic scientists have the weapon in hand, one of the things that they measure is they measure the muzzle velocity of the gun. The way that they do that is actually pretty simple and straightforward. What they do is they take the gun and they basically fire a bullet into a large block of wood. That block of wood is arranged such that it can then swing as a pendulum. And then ultimately you use a combination of the conservation of energy and the conservation momentum to measure out what the muzzle velocity of the gun was. So we're going to do this here as a simple example involving the ballistic pendulum. Let me go ahead and move my file. Okay, so let me read the problem here to you, and the numbers that are given in this problem are reasonable for a situation involving a ballistic pendulum. Okay, so a bullet has a mass of 20 grams, so that's a small caliber handgun or something like that. And the bullet is fired horizontally into a block of wood, which has a mass of 5 kilograms. Usually the block of wood is pretty large. Okay, the block of wood is arranged, is attached rather, to a string that is 1 meter long as a pendulum. Okay, after becoming embedded in the block of wood, so it's a perfectly inelastic collision, the bullet block combination swings such that a 30-degree angle is formed by the string with respect to the vertical direction. Okay, using this data, what we're then going to do is measure out the initial velocity of the bullet prior to striking the block of wood. That's basically the muzzle velocity of the gun. So as we'll see, it's a two-step process. Okay, so let's draw the situation out. Okay, so let's say that right here is the pendulum and here's the block of wood. I'm going to call the block of wood M2, and that's given to us as 5 kilograms. And then we have the length of string L here given as a meter. Okay, and then right here is the bullet of mass M1. Okay, M1 is 20 grams. If I divide by 1,000, that's 0.02 kilograms. And then right here is the initial velocity of the bullet, V1 naught. This is the unknown here in the problem. We'll assume it's a horizontal velocity vector, by the way. We'll ignore projectiles and so on and so forth. Okay, now think of this diagram right here as the instant prior to the collision. Therefore, the instant after the collision, the situation looks like this. So right here is the bullet, like so, embedded in the block of wood, and then the whole thing has a final velocity. That is after the collision, we'll call it V, that is unknown. And then the whole thing swings, like so, as a pendulum, coming to rest here for an instant prior to swinging back down in the opposite direction. And then what we're given is the angle that is made here by the string with respect to the vertical direction. That's given as a 30-degree angle. Okay, now I'm going to go ahead and put in some geometry here because ultimately there's a height change h that occurs here in this problem. If you recall from conservation of energy when working our way through pendulum problems, the value of the height change h is equal to L minus L cosine theta. So revisit that portion of the lecture back in the earlier portion of the unit on work and energy if necessary. Okay, now we are given this right here as a 30-degree angle. So before we go any further, let's immediately go ahead and calculate what h is by just plugging in everything. Okay, so 1 minus 1 times cosine of 30 degrees for the height h, and that comes out to be about 0.13 meters. Okay, now here's basically our method for solving this problem. What we're going to do first of all is a little bit of conservation of energy here, like a basic pendulum problem, to find this v. And then once we have this v, then like in the last example, we'll set up a situation involving conservation of momentum with the perfectly inelastic collision to find the initial velocity of the bullet. That's basically the idea. All right, so let's go ahead and set up our conservation of energy expression. 0 equals delta k plus delta u. And then we just start filling in our terms. So first of all, the final kinetic energy of the system here is 0. And then minus the initial down at the bottom of the swing with the speed v that we're trying to find. And then we have change in potential energy. So right up here is the final potential energy of mgh. And then minus the initial potential energy of 0 because we begin down here at the bottom of the swing. Incidentally, by the way, in the expression that I just wrote down, the m, technically speaking, is m1 plus m2, but it's actually going to cancel from the expression anyway. So let's go ahead and do the math here. Let's move the 1/2 mv squared to the other side like so. Okay, and then at this point, as you can see, the mass m cancels. Like so, and now we solve for v. So multiply the 2 to the other side and then take the square root. I'll just put this down here at the bottom like so. And we end up with this expression that we've seen before in other situations involving conservation of energy, square root of 2gh. Now the h is still here in my calculator, so times 2 times 9.8. Take the square root of all of that. And then ultimately the speed here at the bottom of the swing is 1.62 meters per second. So you look at that speed and then you say to yourself, oh, okay, well that means then ultimately the speed of the bullet here probably is going to be pretty small. Not so. As we'll see, it's actually going to be pretty large. This is a realistic situation. And the reason for that is because the mass of the bullet, M1, is so small compared to the block of wood. And now what we do is we examine this portion of the diagram here, and we set up our conservation of momentum expression. So now change in momentum of number 1 plus change in momentum of number 2 is equal to 0. And now we start filling in all of our terms. So first of all, the change in momentum of the bullet. Its final momentum is going to be m1 times v, and then minus the initial, which is m1 times v1 naught. And now we do the same thing then for the change in the momentum here for the block of wood. So its final momentum is m2 times v, and then minus the initial momentum of the block of wood, which is 0, because that begins at rest. Like so. And now what we do is we solve for v1 naught. So let's take this quantity and move it to the other side, like so. Okay, let's add together these two quantities here by factoring out the common v, like so. And then notice that this expression is similar to the cart problem from a little while ago. But now what we're solving for here is the initial velocity of the bullet. So v1 naught ends up being the following. Okay, now because m1, the mass of the bullet, is pretty small, this is why you can begin to see that that velocity, v1 naught, is going to be pretty large. All right, so let's see. I've got the V here still in my calculator from earlier. So now I'm going to multiply by the total mass. The total mass is 5.02 kilograms when you add things up there, like so. And then divide by the mass of the bullet, which is just 0.02 kilograms. And ultimately, I end up with about 406.7 meters per second. This is actually a realistic number. It is, in fact, above the speed of sound. So then, therefore, this is one of the methods that forensic scientists use to measure the muzzle velocity of a gun. There's another way in which they can do this, which is more or less the same idea. Instead of firing the bullet into a block of wood, which then swings as a pendulum, what they do instead is they then fire the bullet into a block of wood, which compresses a spring. And then they use conservation of energy, blah, 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 conservation momentum, to ultimately measure out the muzzle velocity of the gun is. Okay? All right, so that's the one-dimensional, perfectly inelastic collision. In the next lecture, we'll take a look at the two-dimensional, perfectly inelastic collision.